Is really that the aspect ratio between height and width is changing. So why would that matter? So now let's look at a simple particle in a box model. We know how to compute that. It's basically h bar squared over 2m star over 1 over base square plus 1 over base square plus 1 over height square, right? So the baseline shows up twice and the height shows up once. That's a simple particle in a box problem. If you take this equation and take the ratio or the differential with respect to height and base, you can define this in terms of an aspect ratio of height over base. That means that if you change the height, it has a significantly larger effect because it's 0.5 times aspect ratio to the third power than the base width. That is only true if the aspect ratio is less than 0.3, which is the case here. What that means is if a quantum dot is very wide and very short, changing the height a little bit has a dramatic effect. Why is that? Because that's the critical dimension that determines the ground state. The lateral size, you can wiggle that a little bit, it's not going to change the lateral confinement. But changing the critical width, which is the short one, by a little bit can change dramatically the confinement. So if you plug in some of these numbers, where you say, okay, I'm going to, from that calculation we had a base width of 22.15 nanometers and a height of 5.43, we can get an optical gap of 1.1. If we just make the base width a little bit smaller and the height a little bit larger, like we measured from the strained atoms, we get a gap of 0.95. The difference is 60 millectron volt. That's a pretty large distance for electronic structure calculations. And if you put these things together now, here was the base and the height variation, here's the corresponding aspect ratio variation. The base goes down, the height goes up, that means the aspect ratio goes up. We have this little analytical formula that we understand now. That means overall, the way the eigenstates are going to redshift, meaning the band gap is getting smaller. So here's this aspect ratio change model. If you make the indium concentration larger and put in more indium into the buffer layer, the aspect ratio gets larger. That results in a band gap decrease. And here's what was measured experimentally. So it's not quite enough to explain it by itself either. Right? Just changing the aspect ratio doesn't change enough. So, but you guessed it right, if you then also put in the strain model that gave you an analytical shift, if you put it together, you roughly get the right thing. So, once you knew how the atoms moved, and once you knew how the band edges moved, you could derive an analytical model that gives you the gap. The question is, how would you do that without a numerical simulation? I don't think that's quite as easy. But let me overlap, so we can just sort of forget about the individual results, and now we have the experiment and this analytical result, and we can overlay the NEMO result that comes out of box. So we roughly agree very nicely, I would say, actually, with the experiment. And we also now understand why we agree with the experiment. We understand the physical phenomena that are under the hood. And NEMO allows us to be sort of the probe that looks inside the system and measures how these atoms have moved, what the strain is, what the band edges would be, and we can use it as an analytical tool to really understand experiments. And then the next step is, can we use it to design, to do better structures, right? That would be part of TCAD. Another effect that you need to be aware of, that the bands are really non-parabolic. In particular, indium arsenide is very non-parabolic. We had that in the resonant tunneling diodes as well. So that means what you thought would be a parabolic nice band, the heavy holes and the electron bands are very non-parabolic. What you can do is you can quantize these K points depending on the size of the system and make it a sort of a K-dependent effective mass. That's one way to make this non-parabolic. And you can build that into some analytical model like that to get the right estimate for the redshift. Finally, you need to ask yourself, why is there a nonlinear behavior in this experiment and theory? As you remember, here, this curve is not just a straight line. Why is it so nonlinear? What you can plot here is that the conduction band states all move rather smoothly. So eigenstates in the electrons, there's no nonlinearity. But the whole states move rather nonlinear. You can ask yourself, why is that? Since the conduction band states are pretty much just functions of the hydrostatic strain, and it's happening linear, and you know that the hydrostatic strain therefore must be rather linear. The whole states, the heavy hole states, depend on the hydrostatic strain and the biaxial strain. Therefore, the biaxial strain must be very nonlinear. Indeed, if we plot the hydrostatic strain, it's rather linear as a function of indium concentration, and the biaxial strain looks nonlinear. So what does that mean? Where does this come from? It really has to do that indium gallium arsenide is not a homogeneous mixture in terms of its bond length. Indium arsenide likes to maintain its indium arsenide bond length, and gallium arsenide would like to maintain its gallium arsenide bond length. And you'll see that in the next presentation when we talk about alloy disorder in indium gallium arsenide, how these two materials actually build a bimodal strain bond distribution. Locally, indium arsenide would remain to look like indium arsenide. It's not going to take on an average bond length. It's going to look like indium arsenide in terms of distance. Then if you move over a little bit, the gallium arsenide will be shorter, and it likes to look like gallium arsenide. It's a rather inhomogeneous system. It's not an average bond length.